All right. Good afternoon, everybody, at least those of you who are in Europe. Or in our time zone or nearby. Alexander just sent a nice chat saying that he sees the title as a very promising. I think so too. I think what you can do with the combination of Spine Toolbox and SpineInterface is very nice when you want to build new models. And today we will be exploring that. It will be presented by Jody Dillon from Energy Reform and manuelmarin from KTH. I will not steal their thunder. They have lots of really nice things to show. I will still go over a little bit of the other stuff we have here. Our project is funded by European Union. I think most of you have been already this week, so I won't say more of that, but thanks EU. It was very nice to be able to do this. And we've had the webinars this week, and the webcasts will be available in YouTube next week, and we'll send you a link to all of the recordings next week. Then, as before, we will be recording this webinar, and you are muted, and we can let you speak if there is a need be. Put a hand up, and we can do that. Preferably, let's do the questions during the presentation in the chat, and we can answer the technical questions, and then have a Q&A afterwards for all the questions that are better discussed. And you can, of course, then ask more during the Q&A, both ways, by speaking after we unmute, or then through the chat. So without further ado, I will let Jody take control of the presentation.
Great, thanks very much, Juha. So the agenda for today's webinar. It's divided broadly into two parts. I'll take the first half, which is an overview of the motivation behind SpineInterface, what we're trying to do, its context, its role within the context of the toolbox and SpineOpt, and what it can do and what it was its function is. And in the second part, it'll be more of a live demo from Manuel, giving you a real hands-on feel for what you can do and how quickly you can do things with Spine Toolbox and SpineInterface together. So that's broadly the structure of today's webinar. So by way of motivation, you've probably heard this story a few times already. But we've been, most of the partners involved and the individuals involved in Spine as a project have been modeling for many years, even in decades, and particularly modeling the impacts of variable renewable generation. And as we go into the energy transition, we see that some of the tools we have struggle to adequately capture phenomena associated with the energy transition. So as we have seen more renewables and more electrification on the system, they pose challenges in terms of operating, planning the system, and consequently modeling the system, for example, uncertainty and variability. And that creates more interactions across time, across sectors, and across regions. So, for example, the need for flexibility on the system at short time scales impacts the investment value of technologies which are very long-term decisions. And another thing that we've seen is often the design of tools. So we've been using models, we've been developing models, and what we've seen often is that early design decisions in our tools eventually start become limiting and prevent us from really capturing a lot of these things very easily. We start having to hack things together, link things together in ways that maybe are a little suboptimal. And also new technologies that we never foresaw when we developed our tools are difficult to model with what we have. So both our models and our workflows become more complex. There's more data, more processing, more linkages between different models, that kind of thing. So our models and our modeling tasks are becoming more complex. So this is the kind of high level motivation for Spine. And if we look at Spine in terms of kind of the traditional modeling demarcations that you would typically, we would have had markets and operational type modeling that focuses, hourly type modeling, maybe looking a year at a time, tools like Plexus and other things used in that sort of space. And then we would have longer term models, investment models, perhaps like Balmoral, tools like that. And then energy system models that have broad scope. And typically we see that as we increase the scope in terms of the sectoral scope and the temporal scope, it generally speaking means our optimization problems become a lot larger. And generally speaking, we need to sacrifice a lot of detail in order to increase the scope. But the problem is with the energy transition, increased renewables, electrification, sector coupling, we see a lot more interactions between these things, like the need for flexibility influencing investment value of technologies, or technologies like hydrogen that link sectors together, that sort of stuff. And so the traditional modeling demarcations sort of become less useful. And so that was another driving force behind Spine. And with Spine, what we've ended up with, and this was the objective, is that a Spine model can essentially be any and all of those models, depending on how you set your model up. And we've achieved that in a number of different ways. So in terms of Spine Toolbox, we have a comprehensive workflow management system that enables us to link more models and tasks together coherently, methodologies and features and tools to capture more scope and more detail at the same time. For example, decomposition or enhanced representative days, etc. And a model SpineOpt that incorporates the state of the art while dispensing with the traditional demarcations. But also a key enabling factor in all of this is a system design that is flexible, problem independent, and easily extendable, because we assumed from the start that we don't know what the problem of tomorrow is. So we've tried to design this system with that in mind, so that it can be not only useful out of the box, but bearing in mind that it's definitely going to need to change over time. And so to make that easy, and SpineInterface is a key enabling factor in achieving this goal. So this slide just captures some of the elements within Spine, and you've probably seen a version of this already. And what we want, a key aspect in all of this, is that we have Spine Toolbox, which consists of many different elements, and all of which have been designed to be problem independent and flexible, so that they can be used for any modeling task, even outside of the energy sector. And so, for example, a problem independent data source, data structure, and with an API to interface with that, and a user interface. And SpineInterface makes the link between this data and these functions with a Julia model in a very powerful way, and we'll come to see how that works. So we've seen already the webinars covering these, and as you've seen, there are the links will be available to the recordings. So that's just kind of the problem that SpineInterface is trying to solve. If we look at a typical model structure, so Eventually, what we're trying to do usually is we have some sort of idea. Our model, generally speaking, consists of the set of constraint equations if we're using optimization. And usually this is where the special sauce is, the innovation, the ideas that maybe it's a new algorithm, a new problem structure, a new formulation, who knows. But generally speaking, we need data for our models, and we have to decide how to store that data, and what structure to store it in. And we also need a way of getting that into our models. And very often you find that because the model is where the innovation is, that's what we're interested in. Very often we take shortcuts in the design and the interfaces that become limiting in the long run. And then it's nice, but not always a necessity. But it's nice to have a graphical user interface to manage your data and to talk to your data, to interface with your data. So very often what happens is that because often we don't have the luxury to focus on these almost ancillary elements, very often there's problem-specific elements there that mean when we want to do something new with our model or change our model, we have to go back and change things in here because there's some stuff that's built into the design. And also, when we have an idea for a new model, often, we don't want to have to reinvent the wheel by developing all this stuff. What if, someone could provide that, for us? And that's what Toolbox essentially is. And what Spine Interface enables us to do is jump straight into the model. So this is how we do this. So let's say we have our Julia model using jump, for example, and Spine Interface provides a direct link to the data. And because this data structure and the API and the user interface and all of that is problem independent, it means that when we want to change our model, we don't need to change any of these things. So in fact, how it works is when our Julia model needs some new data or needs some new structure, we can define that all within the SpineDB Editor because the structure and the data is defined there. And then all of the rest remains unchanged because it's designed to be that way. And we'll see how that works now in the next few slides. So, what Spine Interface essentially enables us to do is that, let's say we have a model, and usually models contain sets or entities or whatever that represent physical things. So, for example, just say our model needs a new entity type, a unit. That's going to be a set or an entity type within our model. So all we do is we add that object class to our data store within Toolbox in the DB editor. And straight away, we get access to what we call a convenience function within Julia that is a reference to this entity. And I'll explain a little bit more how that works. So basically, it's as simple as I need a new entity or class in my model. I just add it to SpineDB Editor, and immediately I have access to it in Julia without having to change any queries or change any interfaces or anything like that. So the key to enabling this flexibility is a problem-independent data structure, and so we use what's called an extended entity attribute value structure. So that consists of object classes, and an object class is going to be, as I said, something like a set or an entity class in your model. So an example of that might be a unit or a node. It's a generic high-level thing. But then we have objects, and objects are instances of these object classes. And so an example of an instance of a unit is, let's say, coal unit 1 or CCG unit 2. An instance of a node might be electricity or natural gas, for example. Then we have relationship classes, and relationship classes tell us how these object classes are related to each other and what kinds of connections you can make. So for example, let's say we define a relationship class that's between a unit and a node, and we call it unit from node. That's saying it's possible to connect a unit to a node in our model, and that has some meaning. And the meaning, let's say in the example of SpineOpt, is that we trigger a flow, an energy flow from the node to the unit. And then we have relationships, which are specific examples of these relationship classes, or it's a relationship, it's a specific connection between specific objects. So, for example, let's say we have a unit from node between natural gas and CCGT unit 2. That's telling us essentially that this unit consumes this fuel, for example. So that's an example of a relationship. And so this kind of object classes, objects, relationship classes, and relationships, they all define our kind of model structure. And then we have data. So we have parameter definitions, which define the data that it's possible to specify for different objects and relationships. And then you have parameter values, which is the actual data, and values for the parameters that are possible to define. So for example, number of units might be a data parameter that you can specify for a unit. And here it's the example of 1. So that's a kind of simplified view of our data structure that enables this flexibility and problem independence. So it allows us to do a lot without changing the design of any of the elements. So just taking as an example SpineOpt's specific data structure. So it has lots of object classes, and these are the object classes that we have in SpineOpt. But if you have an idea for a model tomorrow, you can define whatever object classes you want that don't have to have any relationship with this whatsoever. But this is just what we have gone with for SpineOpt. So these are the object classes that we have in SpineOpt. And then these are the relationship classes that we have that it's possible to make connections between these objects, for example, as I said, between a unit and a node, but also between a connection and a node, etc. And so they're relationship classes we see. But what's interesting here in the example of SpineOpt is that these object classes we see here are they're model object classes. They're not representing, let's say, a system, but more the structure of our model, almost the structure of the algorithm itself. But these object classes here are more of a relationship with physical things and our physical energy system. So just to show that we can use object classes and relationships in many different ways in our models. So here's just how we define that then within Spine Toolbox. So Spine Toolbox has a tool called SpineDB Editor, and within that DB editor, this is how we define as a matter of just right-click, add object class, and so here we see our object classes as the same ones you saw in the previous slide. So these are object classes. We see them in a tree view here, and when you expand one of these, then we see the actual member objects. So we can define all our structure within this. And so we also can specify data parameters and give them values within the GUI. And also the same for relationships. We can define relationship classes and also manage the actual specific relationships as well. But also relationships can have data parameters and data, because sometimes data is related to a connection rather than an object. For example, a capacity might be related to the flow between a unit and a node, for example. So that's kind of how then we define this structure within DB Editor in Spine Toolbox. And just to reinforce that we define this structure, this model structure, without having to write a single line of code. So the core idea, or the core core thing, I just want to reinforce here that these when I say connections, nodes, units, they're all just examples of object classes that we've used in SpineOpt. They're just as anyone can have different ones. They're just what we've used in SpineOpt. So the core of SpineInterface are what we call convenience functions. So it's a set of functions that we get arising from our data in Julia. So for example, when we add a new object class, so let's say we add an object class called unit, then straight away in Julia, we get a so named function called unit with the same name as we called our object class. This will basically allow us to iterate through the members or objects of type unit. But right now we haven't specified any unit, so that would just return an empty set for now. But then in DB Editor, we might come along and so add some objects, and let's say we add these two units, CCGT unit 1 and 2. And now in Julia, if we were to call this convenience function unit, and we print out what each of the iterators that it returns or the elements that it returns, we see that we get back the objects that we created in our data store. So as you can see, these convenience functions within Julia are created as a result of our data and give us instant access without having to write any code whatsoever. Similarly, our objects might have data. So let's say we define a data parameter called pmax, and that's associated with the unit object class. We also get a convenience function with the same name that will give us the value depending on the unit. In this case, pmax is a parameter associated with the unit, so it takes as its single argument a reference to a unit which we can get by using our previous convenience function called unit. So this for u and unit will just cycle through the units and give us a reference u to a specific unit, and then by calling pmax with that as an argument, we get the value for that particular unit. So as I said, there's no data there, so that wouldn't be very interesting. So what we can do is we specify some data, some values for pmax for specific units. And here we've given values 400 and 350 for these two units. And if we then call this parameter convenience function pmax and inspect its value, we can see that we've made that connection between our data and the code. And also note this additional function called indices. And so what we could have done is we could have iterated using the unit function. That would have iterated through all the units in the database, but we have no idea whether pmax is specified for all units or not. So this indices function takes as an argument a parameter name, in this case pmax, and will return all the entities, in this case units, for which that parameter is defined, which is quite useful. And that gives us a convenient way to manage ambiguity and missing values, for example, so we don't get errors. Yeah. So then similarly, relationships, we got similar convenience functions. So if I add a new relationship class, and so this relationship class is, let's say it's between a connection and a node and a node. So it's basically specifying a connection and it's to and from node essentially. And this is a three-dimensional relationship, but we can create relationships of any arbitrary dimensions. In this case, it's 3. And so this we've named this relationship class connection node node. So then we get straight away in Julia a convenience function with the same name. And in this case, because it's a relationship, what this will return is an array of tuples that are all that represent the relationships of this relationship class. So for example, you'll get an array of sets of connection node and node that are part of this relationship class. But also what we can do is if we have, let's say we have a connection object class, and we get a convenience function called connection, and that will return all the connections for us. So if we have a specific connection C, we can also use this relationship convenience function connection node and filter it by this connection to see what other relationships it's a part of and what the other two nodes are. So these relationship convenience functions are very useful for managing multi-dimensional relationships and structure in a model. So again, so this is defining the relationship class, but we don't have any relationships yet, so these will just return empty arrays. But if we created a relationship called connection, if we created a relationship between this connection called connection 1, 2, and this node 1 and this node 2, it's basically saying that this connection 1, 2 goes from node 1 to node 2. And so we can specify that data. So this is an example of a specific relationship of this type. And so when we run Julia, or we call this convenience function connection node, in this case, we only have one relationship of this type, and it just returns the single tuple consisting of connection 1, 2, node 1, and node 2. So that's the single relationship of that type. So that's, and similarly, we can define data for relationships. And so in this example, we've defined a data parameter called capacity, and capacity is associated with a connection node relationship. So similar, we saw that before. Pmax was a capacity, it was a parameter based relating to just a unit, and it just needed a single argument. But because this capacity is related to a relationship, it needs multiple arguments consisting of the members of the relationships, and in this case, connection, a node, and a node. And again, we see here how it's convenient to use this indices function. So when we call indices and the argument, the capacity parameter, it will return to us, in this case, the full set of indices, an array of tuples, each one representing a set of indices for capacity. So another thing that we have that is quite powerful in Spine are method parameters. And essentially a method parameter is a data parameter, but that can only take on a certain number of values. So in this particular example, I've defined a method parameter called a unit type. And unit type may take on any of the values: unit type thermal, unit type hydro, unit type renewable, unit type other. In this particular case, but you can define whatever you want, any method parameters you want. And then we instantly get in Julia, what we can do is filter our objects by this parameter and its value. So in this particular example, I've called the unit function, and the unit function without any arguments would return all the objects of type unit. But when I include here this optional filtering argument where I specify unit type equals unit type thermal, then this function only returns the values for which that is true. So this is a very nice way to filter and also create subsets. So we've effectively created a subset of the set of units which equate to the thermal units in this particular example. And so we can also define them for relationship classes. And so they're also a convenient way to we can use this as conditional, use them as conditionals in constraints. So, for example, here's just a sample hypothetical constraint here, but what we see here is I'm using this filtering functionality to make this constraint conditional. And we notice here also that we can apply as many of these filtering arguments as we want. So in this case, this constraint will only be generated for units where the unit type is equal to unit type thermal and where the has online variable method parameter is equal to true. And these are just figments of my imagination that I came up with for this presentation. So then moving on then to the parameter types in Spine Toolbox and SpineInterface. So these types are implemented at Toolbox level, but SpineInterface supports them within Julia, and they give us a lot of power. So the simplest is a scalar value, and we've seen an example of a scalar value already with my Pmax example. And so Pmax equals 400. That's a simple scalar value, and we know how we would reference that within Julia. But we can also have duration values, and that just looks very similar, where we just specify its type in Toolbox as duration, and give it. So here we see we have a minimum uptime parameter, and it has a value of 1 hour, and that's called in the same way to a scalar parameter. We can also have array parameters. So for example, I've just created this parameter called operating points, and it's of an array type. And we can see we get a little in our parameter value editor in Toolbox. We can enter the different elements of this array. And in this particular case, operating points is an array consisting of 4 values. And you get a little plot of it here. So to reference that within Julia, clearly we need an additional argument now, which equates to the element of the array. So we call it I. And so how do we get the i's? Well, we can just use the length function on the parameter convenience function, as you can see here. So the array type is quite powerful as well. So then we have a few time related or time varying formats or data types. So the first is a time pattern value. So here as an example, I've put in a time patterned value for Pmax, and in the editor you can just define using standard notation for different time patterns. So for example, here just for hours 1 to 12 it has a value of 400, and hours 13 to 24 it has a value of 300. That's just an example. And here, because this is now a time varying value, we need to specify a time index. So in this particular example, so and I'll talk a little bit more about how we manage time in SpineInterface and Julia. But also we can specify time series values, and we put a good bit of effort into managing time series because it's pretty important in energy systems modeling. So we could also have a fully time varying value for Pmax if we wanted in this particular case, and you call it in the same way by specifying a time slice argument, and you will be returned with the right value for that particular time slice. And time series, they can be fixed or variable resolution. They can be absolute or relative, and they can be repeating or static, which is almost the same thing as absolute or relative. And they can be plotted and visualized within the app, within the toolbox. So we have a lot of powerful tools for managing this kind of data. And finally, one of the most powerful data types we have is a map type. And this essentially allows us to create two-dimensional arrays where the first element is an index for the second, and each can be of any type. So, for example, we use this type in SpineOpt for stochastic data. And so this, in this particular case, we have a VOM, variable operating maintenance cost, and it's given a map value. And the map value in this case is a map from a scenario to time series. So here we have 4 stochastic scenarios, 1, 2, 3, 4, and for each of those scenarios, there's an associated time series, and we can plot that. And you can see we're using this map type to represent stochastic data, where this value has this VOM cost has a different time series for each scenario. You can see it plotted there. But it's a very flexible type, and you can use it, for other types of data. It's up to you. But how you reference this data is we, of course, need now another argument that in our case is stochastic scenario, but this argument just needs to correlate to whatever you have as your X in your map data type. So that's a very, very powerful type. And finally, what's very nice within SpineInterface is that if I call SpineInterface handles the parsing of parameter types. So, for example, if I call the Pmax function with these 3 arguments, unit, stochastic scenario, and a time slice, I will get the correct value back regardless of whether the user entered it as a static value, as a time pattern value, as a time series value, or as a map value. So by always providing arguments, stochastic scenario, or time size where relevant, it doesn't matter how the user has entered it, and the user doesn't need to worry if you do this whether it's possible within the model or not. So this gives us a very powerful framework for defining data. And so, for example, how we used this within SpineOpt is that we always assume a user may have entered a value as either static, time varying, or stochastic. But of course, they don't need to. So SpineInterface temporals. So we got some tools within SpineInterface to manage temporals. So we saw that for time varying parameters, we need to supply a time size index, which represents the point in time we want the value for. And so SpineInterface provides this time size class that represents a discrete time step with a start, date, time, and a duration. But we also get a load of some helper functions to manage temporals. For example, overlap duration. If we have 2 time slices, are they overlapping? So we're not assuming. So this can handle time slices of arbitrary resolution and duration. And so to manage that sort of thing, we need these kind of helper functions. The roll function allows us to roll our data and our time slices backwards or forwards, and Manuel will show a little, I believe, how that's very useful. And also sometimes when you allow this, or when you're dealing with data of multiple or varying resolutions, you need to be able to resolve inconsistencies in resolutions. And so, we functions like T lowest resolution, T highest resolution, for example, that allow us to manage those. So we do get some tools within SpineInterface to manage our temporals and create a structure for time varying data. So SpineInterface API. So up until now, I've been showing how SpineInterface So Spine Toolbox allows us to define our data structure using DB Editor by creating our object classes of any name we like, parameters of any name we like, and create relationships between any of those object classes and objects, and define data for those, etc., etc. But SpineInterface also has an API that allows us to create this data as well, and that could be very useful. So we can create new parameters, objects, relationships. We can manipulate them. We can create new data stores and brand new, completely new data structures using SpineInterface. So essentially, anything we can do using the DB editor, we can do within Julia using the SpineInterface API and create data sets on the fly. And what that does, it gives us access to Julia's scientific computing capabilities and its high performance for doing a lot of scientific computing. And so it allows us to develop tools within Toolbox that process data and link up with the Spine data structure. And some ways in which we've used that, here's an example where we've got in SpineOpt, we implement decomposition, and decomposition consists of a master optimization problem and a sub problem. And when the master problem solves, it produces a solution, and it needs to pass information by way of the values of the decomposed variables. And we do that by using the SpineInterface API to create new data parameters that are inputs to our second model. Then our subproblem runs and it produces results. And what we need to then pass back from the subproblem to the master problem are some constraint dual values. It does that by also creating new SpineInterface parameters using the API. So that's a very nice, practical utilization of the API. Also, this is an example from VTT Finland of how they've used Spine Interface to process data, where they have data coming from a lot of different sources relating to buildings and building archetypes and building modeling. And they link to that using a Julia tool that uses SpineInterface, and it processes all this data using SpineInterface and Julia's capabilities, and then produces a brand new data set as a result of using the API. It creates the whole a set of object classes and relationships that are needed to create the new data structure. And so this is, for example, how it would the result of this looks in the finished case. So you can see that this entire data structure has been created from within Julia using the SpineInterface API using a set of convenient functions. So that's quite powerful. And so this is my slide to wrap up. So basically why SpineInterface and why Julia. So if you have an idea you want to create an optimization model, for example, why would you go to the bother of creating user interfaces, data stores, data structures, when you can just jump straight into writing your constraint equation codes and benefit from the work that's gone into the Spine Toolbox and data structure and DB Editor, etc. So you essentially will get for free a user interface for your model that you're going to use. And the benefit of using Julia for creating optimization models is, for example, unlike GAMS, which has its advantages, but it's just it has some programming functions, but is mainly designed to express algebraic expressions, etc., to define a model. But using SpineInterface and Julia, you get access to Julia's programming capabilities, scientific programming capabilities, which we found to be very useful. So you can define your data structure that you need for your model in SpineInterface, and DB Editor, etc., and then gain access to all the data management and workflow management tools within Spine Toolbox. And it also allows you to link your model with other tools and models within Spine Toolbox if you've developed it within Julia and using SpineInterface. So thanks very much. I hand over now to Manuel.
Hi, thank you, Yori. Thank you so much. Very nice. Thanks everybody for attending. My name is manuelmarin. I'm with KTH in Sweden, and I will be taking the rest of the webinar. So I'm sharing my desktop now. I hope you see the Spine Toolbox interface. Not anymore. So I have just a couple of slides. I will be taking these two sections here, defining a model data structure in a Spine Toolbox, and building and solving an optimization model using SpineInterface. And I will take the two at the same time using a demo in a Spine Toolbox, so you can see how this may work. So this is the Spine Toolbox main interface. Yeah, you see we have like different components here, but this is where we define our project, which is basically a workflow composed of different items that are connected together in order to define a modeling exercise. And I will start by creating a database here. I will use an SQLite file for now that I will call datastore1 SQLite. So here I have a data store, and I can double click this item to open this DB Editor interface that we use to visualize data in Spine format. And as you see, this is empty. I will start adding stuff now. So I will begin by adding some object classes. And I will be trying to define an energy system model that we can optimize to see results. Let me select some nice icons for this so we can okay, bus. Okay, so now I have these two classes here that I can start filling with objects, with actual objects. So I will do that. I will add a couple of nodes, and I will just call them node 1 and node 2. Sorry for lack of creativity. It's just so this is pretty simple to follow. And I will also create a couple of units. And again, I won't get any creative here. They will be called unit A and unit B. So we have some content in this database. I will commit commit changes to the database with a message, a meaningful message. And now I will create a tool that will process this data set. I will just call it tool1. And I will connect the data store to the tool like this. And I will pass the URL of the database as a as a command line argument to the tool. So now this data store is sending its URL to the tool. And if I double click the tool, I get this interface where I can define what this tool does. So I need to enter a name for this tool specification, and it will be a Julia tool. And I will create a file, and I will just call it demo.gl. And this is the file that this tool will execute when I execute the project. So I will bring the SpineInterface package we have been discussing, and I will define this variable that I will just call URL. And as I was explaining before, it will be the first argument from the command line because I have this connection here. And then I will call this function that is provided by SpineInterface, that is basically receiving the URL of the database, and it's creating all the so-called convenience functions to access the contents of the database. So I save everything. I execute the tool, so I get a console with the output that I can also interact with. So this is probably compiling a SpineInterface just in time. So now it ran, and now I can call node like that, and I get a list of nodes from the database. Like I get these names here. That's all, and I can do the same for unit. I could also add like a third unit, unit C. Okay, commit changes. So now I won't be wasting any time in writing commit messages. And then I execute this again, and now the contents of the database have been updated. So you can imagine, okay, so I'm getting the third unit also when I call unit. So you see how this is refreshed automatically. So it's a pretty nice workflow that you can have. Moving forward, I will create a relationship class between these two object classes. So I will select this object class as the members of the relationship class, and I will call it unit node, like this. And now I can actually, here I can create some relationships between my units and my nodes, and I will just do that randomly. I'm just trying to build something like an energy system here. So, and then let's say that unit C is also connected to node 1, like this. Maybe I also want unit B to be connected to this one, so it's more like a network. So this is fine. I will commit changes again, rerun my tool, and now you can probably imagine what happens if I call unit node. So I'm getting all the relationships I just created as a vector of named tuples. So unit B is connected to node 2, and etc., etc. I could also do something like this. I could define a variable for the node that's named node 1, like this. So N1 now is this node 1 from the database. So I can show you the filtering thing we have. So if I call unit node, where node is node 1, I should be getting back only unit C and unit B, because node 1 is only connected to unit C and unit B. So that's nice. I can also define some parameters. So I want to define some parameters for my classes. So I will define the parameter called demand for the node. And then I will specify demands for my node objects. So let's say that node 1 has a demand of 100 something. And the other node will have a demand slightly higher. Let's commit results, commit changes, sorry. Let's run. And now I can query my demands. So for example, I can ask what's the demand at node 1, and it's obviously 100. And just for completion, I will do the same for my other node. So I first need to create this variable, and then I can just query the demand at node 2, and it's 150. So I will keep going. I will create a parameter called capacity for my unit class, and then I will specify capacities for all my units. So you probably know where I'm trying to get here. I want to write some constraints for my optimization problem. Next. Sorry if I'm going too fast, but hopefully you can understand. This is pretty. I think it's pretty simple, right? Just capacities for the units. Well, maybe we have time to do this again. Let me define this variable, and it will be the unit A. And then I can ask what's the capacity of this unit A. And the capacity is 150. So this is the last thing I want to do in this database. I want to add a cost parameter so I can write an objective function, and I will specify costs randomly for my different units. Let's say unit 1 is, I don't know, 3. Unit B has a cost of 1. Let's say it's cheaper. I'm trying to make it interesting by assigning a lower cost to a unit with a higher capacity. But okay, so we have this energy system set up. We have some demands, we have some capacities, some costs. So we should be able to write an optimization problem for this. And I will do it using the JAMP package that you may have heard about. And I will use the open source CVC package to provide me a solver. And I will create that solver. So I have memorized this function optimizer with attributes that I can use. This is just JAMP API. And I also know that if I use this, I suppress all the output from the solver that I'm not interested in. And I will just create a JAMP model using this solver. Let's run this again to see. Well, I guess this run is mainly just compiling the JAMP and the CVC. Let me add this here so we print the model. Well, it already did because it was the last instruction in the script. So now it's a feasibility problem with 0 variables, of course. So let me add variables to this model, and I will use the variable macro. And I will create a variable called flow for all pairs UN in this unit node relationship class that I have available. And I will say that these flow variables are positive. Let me see if I didn't make any syntax error. Apparently no. So I have a feasibility problem subject to a set of non-negativity constraints here, and I have my variables. So I can now start writing my constraints. So as you can imagine, I want to write a demand constraints for all the nodes that I have created. And it will be just the sum of flows entering the node from all the units. So I can filter I'm filtering the units by the nodes that I'm writing the constraint for. So that sum has to be exactly equal to the demand at the node, something like that. Let's see. So, okay, I didn't make any mistakes, and I see that I have my 2 constraints here. So the flow from unit C to node 1 plus the same from unit B is equal to 100, which is my demand at that node, and the same for node 2. Pretty straightforward. I will proceed now to write the capacity constraint that you might have been expecting, and this will apply for all the units, and it will be very similar, except that I will sum the flow going to all the nodes from each unit, and that needs to be smaller than the capacity of the unit. Let me check that this is correct. Yeah, looks okay. Let's see. So yeah, here I have it. So unit A has only one flow variable, right? Because yeah, it's only entering node 2, and then the other 2 units have 2 flows. So great. I could solve this already. I don't have any objective, but it's a feasibility problem that I can optimize. So let's do that. Well, I guess this won't be very interesting because I probably want to also print the results. So I will do that. So I will do it like this. I will take all the k tuples in the unit node class, and I will print that tuple. I will print a colon. So this is pretty old school result printing. And I will take the value of the flow variable for that key, like this. Let's see. First error here. Oh, it's I'm missing an underscore, of course. Yeah. For k in unit now. Okay. Do I need to do it like this? Let's try again. Okay. So these are my results. I see that unit V is only producing 80 to node 1, nothing to node 2. I guess this is optimal. I trust CVC. But this is not taking into account the cost. So we can take that into account by writing an objective for this model. So it will be minimize the sum of the cost of each unit times the flow on that unit. And I will write it like this. So it's a sum like that for all u and n in unit node. I think this is correct. Let's see. So now you see that I have my objective here. So it's the sum of all the flows times the costs. And I get the same results, which means that the cost didn't matter. But I can try to, like, I don't know, if I want to make it more interesting, let's say that I will say that unit B, let me see. So unit A is actually being used a lot at full capacity, as I'm seeing here. So maybe I can see what happens if I make it more expensive. I have no idea if this is going to make any change. Okay, so now unit A is only providing 50 instead of 150. And then the other 100 are taken by unit C. So that's pretty nice. I can play with my data and run the model again and see the effects instantly. I can also, for example, I like to do this. Let's say that I connect unit A also to this other node, and maybe that changes things. I don't know, but it could be. The point is that it's kind of streamlined. Well, it didn't do anything. Maybe if I disconnect unit C from one of the nodes and run it again, it did something. Okay, so that's that. great. I can actually build a model pretty easily using SpineInterface and Jump and get results nicely or semi-nicely. But I just wanted to show you something else. I can make it more interesting by saying that the demand at node 1 is actually not fixed but a time series. So I will enter a time series with a fixed resolution. So it could be variable, but I don't want to do it like that right now. And to simplify my code, I will use a yearly resolution. And it will be the time series will be starting in the year 2000. And let's say we have 90. And the next year, let's say you have 110, something like that. So I will save my changes. And then here, when I'm querying the demand, I can no longer do it only specifying the node, because it will return the entire time series and it will just fail. So I need to specify the timestamp that I need to that I want to bring for this particular solve. So I can do it by specifying this T keyword argument. And to specify that argument, I will bring the dates package, and I will create a datetime object for the year 2000, and another datetime object for the year 2001. So these are my two timestamps in my time series, if you recall. We can see it again. So 2000 and 2001. And then I will build what we call a time slice. So this is now provided by SpineInterface as well. SpineInterface has an API to build time slices between 2 points in time. So this the entire time slice between the year 2000 and 2001, including the year 2000, but not 2001. So it's open at the end. And I will say that I want to use this time slice for my optimization model. And I will run it like that. And of course, I guess it needs to compile part of the time series API. But now I can see that my first demand constraint is now taking the right value, the first value for the time series, right? It was 90. And then if I want to take the second value, I can do it like this. Let's say, let's roll 1 year forward in time. So, and let's do it again. And now it's taking the 110, right? So, yeah. But this is not great because I need to rebuild the model for every time I want to change the year. And that can be expensive, especially if the model has many rows and columns. So, and it's like a overkill to do that just for changing one right-hand side. So we wanted something more efficient, and we implemented a system to do that. So basically, if you call a parameter function with brackets, it tells Jump and SpineInterface. So it's a SpineInterface that is telling Jump not to evaluate this parameter value right away, but wait until the last minute when the model is generated. And in the meantime, just save this as a call to the demand parameter for this node and time slice. So if the time slice changes, we can reevaluate the parameter value in place without regenerating the entire model again. And we do that like this. So we have this roll function that we can call on a time slice. And I will tell to roll this time slice 1 year in the future. Let me go back to the year 2000 here. And then I will call this update model function on my model. And this will check that the time series has been rolled. So this right-hand side term needs to be recomputed, and the constraint needs to be updated. But only that. Don't regenerate the model. And then let's see what happens. And let's just solve again and see what happens. So let's hope I didn't make any mistake. So you see that we have 2 runs here. This is the first one. And we see that for the first run, the demand is 90, node 1. And for the second run, it's 110. So it's working. And this is very fast because this is a toy model, but for a large model, you can really see a huge performance improvement by doing this in-place model updating rather than generating the entire model again. So now I could go. I want to just show you that I could go a bit crazy here and have many data points. Let's say I have demand for 6 years in the future, and I will. This is just for fun. I will just write a loop like this, as we do in SpineOpt. So I will roll the time slice 5 times. And for each one of these 5 times, I will just update the model and solve the model. So roll, and then I will just print this iteration variable, something like this. And then if I run this, okay, so it only rolled 5 times, but anyways, you can see that for the first run, the demand was 90, and then it's taking the data point from the time series I have defined, and it's running multiple optimization problems. I don't know what happened with the last one. I might want to check that. But I guess you get the idea. So for example, for rolling horizon optimizations, you can use this, and this is what we do in SpineOpt, and you can have a very nice speed up. So that's the end of my demonstration. I have one more slide if I have time. It looks like I have 1 minute for this one. But in case you are curious how we implemented all this in Julia, I have some code here that we can look at just to see how this is all possible. It's pretty simple. So I will explain how it works for object classes. You can imagine that something similar is done for the relationship classes and for the parameters. So Julia allows you to define like these structs that can have fields. So we defined 2 structs here. One is called object and has a single field, which is the object name. And the object class struct has a name field as well for the object class name. But it also has an object field, which is an array of values of this object type. And in Julia, you can also implement the call operator. So what happens when you call an object by adding this parenthesis after the name of the variable. And in this case, when you call an object class, it returns just the array of objects that is stored in this object class value. And then the only remaining thing to explain is how from the contents of a Spine database, we create these objects, callable objects in Julia. So that's implemented in the using a SpineDB function that receives the URL of the database. And let's say you have this function here that it's called, I'm calling object class query, that gets the URL and just yields all the names of all the object classes in the database. So we loop over all those names, and then we build the array of objects. And it's basically an object with a certain name, and the names we get them from another query that I'm supposing we have that takes the URL and the class name and yields object names in that class. So that's our array of objects. So then we can define an object of type object class with this name and these objects, basically. But this is all local to the function at the moment, so we need to make it available at the global scope, if you know what I mean. And we do that with eval. So this is kind of the way we find it that we could do this in Julia. So eval allows you to define a block of code that gets evaluated at runtime. So when the user calls this function, eval generates some Julia code that gets evaluated at that point and kind of creates the interface that you can then call. And within an eval block, you can interpolate variables in your local scope. So here, what we are saying is that create a variable that's named exactly after the class name here. And so this is a string. And Julia is creating a variable named after that string, for example, node. And assign to node this object class object we have created, and then export it so it's available from everywhere. And that's it. And we close the loop, and that's how it works. So that's pretty much it. And that's the end of my part. I will give the floor back to Juha now for the concluding remarks. Thank you very much for your attention.
Thank you, Manuel, very much. That was great, and Jody. So here you can see again our contacts. Please take contact if you want to know more or thinking about some kind of a collaboration or other way of working with us. But really, let's go to the Q&A. And there is a couple of questions there in the chat. I think at least there's some for Manuel that you could maybe read and try to see if you can give a bit of more information about that question on subsets.
Sure. I'm trying to find it. Returning to the specifics of subsets, right?
Yeah.
Can you please show where are your subsets stored, historic filters? In the database or where? Sorry for pushing. Yeah, not in the database. It's in this Julia struct that we defined. So we have a struct that's called object class that has some fields, right? So I was showing you the fields are the name. Maybe I can just share it again. It's here. So this is not complete. I skipped that part for illustration purposes, but here you have like a third field that it's a catch. And as you call this function, and this is also, there's also something here that is basically just to populate this catch field. So basically, you just memorize. So you just take the arguments, and here, okay, so this was really simplified. But here you have the filter arguments. So based on these filter arguments, you can you can filter your objects to return the subset, right? And then you can build a dictionary from filter argument to result that you can check for subsequent runs, subsequent calls, sorry. So you know if you want, you have to return the cached result, or you need to recompute the filter and catch it, basically. And it's all stored in this catch. So it means that if you shut down your Julia, you lose everything. But as long as Julia is running, you kind of have a solution to that slowdown. I hope that's clear.
Yep, seems to be so. Thanks. Are there any other questions? You can also raise your hand if you just want to ask. Meanwhile, Jody, did you have, now that you have some time to reflect on what Manuel was showing, so what do you think we should still say that we've to really highlight the kind of the process of workflow from Toolbox to Julia?
Yeah, I mean, I've seen the benefit firsthand in terms of the work we've done developing SpineOpt. What we found is that what SpineInterface allowed us to do is allowed us to implement very complex things very quickly. So so that was allowed us to do very interesting things in terms of flexible temporal structures and stochastic structures and stuff like that. And it just makes it just developing models. It's a different experience, and from a performance point of view, we find that it compares very well to other models we have as well.
All right, we don't have any more questions, so I think we can be concluding for the day. Thanks again, everybody listening, and for the presenters. Everything will be posted next week, and please share the links once you get them if you had some other people you know who would possibly benefit from hearing any of these webinars. Thanks. Bye-bye.
Bye.